All right, so we're going to be continuing our discussion about volumes and integration, and we're going to continue it by talking about another method to find out the volume, and it's called cylindrical shells. And so, thus far, we've been relying on finding the cross-sectional area with respect to x or whatever variable, and then finding the integral of that cross-sectional area because that represents like an infinitesimally small volume that we're adding for each x value. On a similar vein, instead of finding the cross section, we kind of divide up, in this case, our total volume into cylindrical shells, and then we find out the surface area of each cylindrical shell, and then add that all up. So let's say we have a figure or a volume, or yeah, a figure that looks like this. And for cylindrical shells to work, we need the figure to be symmetrical across an axis. So going back, we have this figure which has like two peaks. And this middle part is not part of the figure. And this is just like a 2D projection. Imagine like a 3D sort of figure that looks like this. And that figure is formed by rotating this portion, this hump that I have across the y-axis, and that's why we have a symmetrical shape across the axes. So you can kind of imagine that if I wanted to find a cylinder over here, I would take some x, right? And then the corresponding x on the other side would just be the same length. So I have a cylinder. I form a cylindrical shell by having some distance from x, and then so our cylindrical shell kind of looks like this. And actually, let me use a different color. So at a particular point x, I'm forming a cylindrical shell, and if I were to find the surface area of this shell, right, that would tell me what area of this region or this cross-sectional region corresponds to words. And the reason why like all of this area is also included is because I have this figure that's rotated across the y-axis. So you kind of have that 3D shape. So we also have like this whole entire part as part of our volume. And so we form this cylindrical shell, whose like surface area is all part of the total volume of our figure, and the the surface area is just given by 2 pi times the shell radius multiplied it by the shell height. Our shell radius is simply how far away our x is, because that's the radius. So it'll be 2 pi times x, and then the height is just whatever this f of x function was, right? So 2 pi times f, 2 pi x times f of x kind of forms this new cross section in the cylindrical shell method. And if we were to multiply this cross section some by some like thickness, and we can call that thickness dx. So I have this cylinder, and then I do a little dx over here. Then you can kind of think about me adding an infinitesimally small volume that represents that represents a slice of volume in my larger figure. And so now I have this cross-sectional area determined by 2 pi x f of x, and then I'm adding this dx for the volume. And if I were to do that over whatever 0 to this final like x2 value is, that would give me the entire volume of the figure, because what I just did is I split up the entire figure into different cylindrical shells, and then for each shell I found an infinitesimally small piece of surface area for that shell and multiplied it by dx to get that volume that the shell takes up. And adding up those volumes for all the x values that our figure takes on, well, only the symmetric part, because every time I'm going from 0 to x, it also covers the corresponding portion from 0 to negative x2. But by doing that, I'm kind of representing the entire volume, and I'll get the entire volume. So it does take a bit of imagination to kind of understand what our integral is doing and why, at the end of the day, these shells add up towards the entire volume. but hopefully it makes sense intuitively. And this is another way for us to find out volumes, where maybe this method to find it out might be easier than us trying to use the ring or the washer method, because in that case, like if we had this sort of figure, the washer would kind of look different uh because the idea is like how would we represent this cross sectional area um differently from this cross sectional area, and it would make everything much more confusing. So at times the cylindrical shells method is a better way to find out the volume, and it might be the only way to find out the volume of a figure. So let's work with some examples. So this problem says that we have a region bounded by the curve y is equal to square root of x-axis, and line x equals 4 revolved around x-axis. So if I were to draw out what this region looks like, I have some square root of x, and then I'm told that that's between that and x equals 4. So over here we have 4 comma 2. And I'm taking this entire region over here since it's bounded by the x-axis. So this horizontal line, and then this vertical line, and this on the top side I have square root of x. And I'm rotating it across the x-axis, so something like this. So we could use in this case we could define our cross section as like this wash or this ring, and just find out the area of each of these circles and add it up. But for the sake of using cylindrical shells, let's try to use the cylindrical shell method to find out the area of our or the volume of our figure. So our shells, in this case, we would have, when we revolve it across the x or the x-axis, that means our symmetry is across the x-axis, right? So that means that must mean that we would have to be integrating with respect to y, because that would mean that we would have some symmetrical portion on the negative y side. So that tells us that we have horizontal that our interval of integration is on the y side. And therefore, this becomes our height of the shell. And let me actually bring out a different color. So our height of the shell is some function over here determined by 4 minus y squared, because y squared is equal to x. So this is the height. And the radius is simply how far away or how high up we are, and that's just y. So the radius is y, height is 4 minus y squared, radius is y. And you can think about this as if forming this little shell over here, and me adding up all of these like pieces of shells as I vary my y values will tell me the final volume of this shape. So I've come up with the radius, I've come up with the height. I just need to simply plug it into my shell formula. So the integral from y equals 0, because that's where we start, up to y equals 2, of 2 pi times radius y times height 4 minus y squared dy will give me the volume, because this is the surface area, and I'm multiplying it by dy to get the little piece of get the little volume that I'm trying to add up. So simplifying this, I would get 0 times I can take away the 2 pi, and then I get 4y minus y cubed dy. The integral is simply 2y squared minus y to the power of 4 divided by 4 from 0 to 2, and then all multiplied by 2 pi. that becomes 8 minus 16 over 4, which is 4. So 4 times 2 pi is simply equal to 8 pi, and that is my volume. So that was an example of using some cylindrical shells. And it's just another tool for us to find the volume, and sometimes it's much easier to use the cylindrical shells method than to use the ring or the washer method that we came up with, because it leads to easier integrals. And so the problem just becomes a choice of recognizing which method will make the life easier. Will make your life easier when you have to find out the area, or I mean the total volume. So that was cylindrical shells. Now let's talk about other general cross sections. So cross sections don't have to necessarily be like a constant shape. Like so far we have dealt with squared cross sections, we have dealt with circular ones because we keep revolving across an axis, or we dealt with like washer cross sections, right? But that's not always necessarily the case. You can have a cross section that is also a function of x. So a cross section that varies with x or y, and that does not take away from our ability to solve for the volume of that figure when we or the shape of the figure. So for an example, let's say that we have a shape whose base is the region between x-axis and one arch of 2 sine x. Each cross section is perpendicular to x-axis and is a semicircle whose diameter runs from x-axis to curve. All right, so given that, we want to find out the volume of this figure. So what this is saying is, let's say we have the base. So the base of like our shape is the region between the x-axis and one arch of 2 sine x. So if I'm drawing out that base, I get at pi over 2, and then this is pi. That is not symmetrical, right? So I get this pi over 2 and then at pi. So that forms one arch. So that's the base, and at each sort of x value, I have a semicircle whose diameter runs from the x-axis to the curve, basically. So this is like one diameter of the semicircle, and I have something emanating above it, and that forms my shape. So you can kind of think of it like that. The base is this sine graph, and then at each sine graph I have these outer semicircle volumes that are protruding out. And given that's the shape, I want to find out the total volume. And so the fact that the volume is just the integral of the cross-sectional areas all like integrated across the region still remains. So our region that we're worried about is from 0 to pi. So that's the region. And now the area of each of these cross sections is kind of made easy by the fact that they told us these are just semicircles with the diameter with diameter given by essentially f of x. So one second. Yeah. So f of x is our diameter and the shape is a semicircle. So what's the area of the cross section? So we know that the area is just pi r squared divided by 2 since we're dealing with semicircles. R is simply f of x over 2. So f of x divided by 2 squared times pi over 2. That gives us f of x squared pi divided by 4. And that's our area. Plugging this into our formula, f of x is 2 sine x. So f of x squared is 4 sine squared x. But multiplying it by the rest of the constants, we're left over with pi times sine squared x. And so we're asked to find the area between 0, or that's our cross-sectional area. So a of x is simply equal to pi times sine squared x. And we know that the volume is simply a of x times dx, so pi times sine squared x dx. And so this integral represents the volume of our shape. And so whenever we have a general sort of shape, we have to go back to the basics and find out what a of x is. That will help us find the volume, because if we multiply a of x times dx over this entire interval where the shape lies in, that will give us the volume. So all in all, we have learned multiple methods to find out volumes of various figures. We saw pretty general cross sections, such as like a circular one, like a washer. We also learned about things like the cylindrical shells method, and then we also dealt with a general non-regular cross section. And hopefully all of these sort of examples made you like learn about all the different ways to find out the volume of a figure.